Hello everyone, my name is Xue Kang. I'm a staff engineer coming from DiDi. My team is responsible for the infrastructure, deployment, tuning, and operation of streaming jobs of the whole company. It's a pleasure being here to share our experience about Flink. And sorry for giving this talk via video due to the COVID-19 situation around the world, and I wish all the best for you. Okay, first of all, I want to introduce the roadmap of this talk. I'd like to describe the overview of Flink service at DiDi first, and then StreamSQL, the major programming language for stream processing. After that, I'll introduce our real-time computing platform, which provides Flink as a service. At the end of this talk, I'll discuss the challenges we are facing now and our planning for future work. So first, let's look at the overview of real-time computing development at DiDi. This is the development history of stream computing at DiDi. We started using stream processing at the year of 2016. At that time, our developers from business teams built many small clusters by themselves, and they tried many different stream computing engines, such as Storm, Spark Streaming, and Samza. They actually spent plenty of time and energy on cluster operations as well as streaming job development, but unfortunately their effort did not really pay off. The good news was from the year 2017, as an infrastructure team, we developed a unified real-time computing service, supporting two computing engines, which are Spark Streaming and Flink. The business teams migrated their streaming jobs to our unified clusters and left the cluster operation jobs to us. And from that time, they could 100% focus on their business development instead of taking care of the big data infrastructure. And of course, in this way, the business team and us worked together much more happily and effectively to deliver better services to our customers. In the year 2018, the number of streaming jobs scaled rapidly, and since more and more new-coming developers were not familiar with real-time computing or Flink's API, we built StreamSQL based on Flink Table API. With this new StreamSQL, developers could develop their streaming jobs quite easily in SQL. And what's more, we applied Flink CEP in our online business scenarios and achieved quite good results. Then in 2019, Flink became the only stream computing framework at DiDi, and without any doubt, StreamSQL became the most popular stream programming languages as well. At late 2019, we began to build real-time data warehouse, and at the year 2020, we will continue to build the data warehouse and explore real-time machine learning. Nowadays, Flink is widely used at DiDi, and this is the current scale of our cluster and streaming jobs. We have been serving more than 20 business teams, and the cluster scales to more than 1,000 nodes. More than 7,000 Flink jobs are running on this cluster, processing about 2 trillion records every day. Real-time computing has rich application scenarios in DiDi and can be classified into 4 categories, including real-time monitoring, data delivery, real-time feature extraction, and online business. In real-time monitoring, for instance, Flink could be used for monitoring metrics of online transactions, such as the number of orders processed so far of the day, or the number of drivers online at this moment. In real-time delivery, all the bin log or business logs are collected to message queues like Kafka, and then Flink jobs are executed to consume these messages from Kafka, and they are sent to HDFS or Elasticsearch clusters. For real-time feature extraction, we know that as an e-hailing company, DiDi collects tons of trajectory data every day. And all these data must be extracted in real time to help improve not only the efficiency of traffic or the experience of our customers, and also the safety of all our passengers and drivers. Navigation service is a typical example. By running Flink jobs, our developers could extract relevant features in real time from the trajectory data to help improve the navigation service. For instance, these features could be used to judge whether a road is jammed or not, and according to the result, more reasonable route can be recommended to the driver. And also, by using these real-time data, we could help improve our real-time business. For instance, by detecting that a car is deviated from its scheduled route, we could, sorry. For instance, these features could be used to judge whether a road is jammed or not, and according to the result, more reasonable route can be recommended to the driver. And also, by using these real-time data, we could help improve our real-time business. For instance, by detecting that a car is deviated from its scheduled route, we could detect the possible hazard or danger may be happening. And then we may send some emergency call to our customers' families or friends, or take some other actions to ensure their safety. Okay, next let's take a look at the architecture of DiDi's stream processing service. There are several Hadoop clusters in different IDCs, but we built a yarn router to unify the view of all clusters. So there is only one logical cluster to the computing platform and users. In an individual physical cluster, jobs with higher priority is isolated with node labels, ensuring that those jobs will not compete with each other to guarantee stability. And other nodes of the same node label, jobs are isolated by C groups. Because streaming jobs are different from batch jobs, such as MapReduce jobs or Spark jobs, we customized a balance scheduler for streaming jobs, which is different from fair scheduler or capacity scheduler. It has following characteristics. First, we suppose that all resources of the streaming jobs demand should be satisfied if the yarn queue's resources are sufficient. With this assumption, resource preemption or preservation is no longer considered. Secondly, streaming jobs are more sensitive to CPU and system load than batch jobs, so our new scheduler allocates resources based on logical CPU. Thirdly, if some node has much higher load than others, it will be recognized and labeled, and therefore no more containers would be scheduled on it. This protects the jobs from running on slow nodes. Lastly, to improve the efficiency of resource usage, a new and more reasonable resource configuration will be computed and generated when the job is running. We achieve this by collecting a job's consumption of physical and logical resources during its running time. And when this job is restarted, the newly generated configuration will take into effect. This also allows all the jobs and clusters to run in a much healthier manner. Next, let's go into practice of StreamSQL and DiDi. StreamSQL is built on Flink table API. In the year of 2018, we were using Flink 1.4, which did not support DDL. Users had to write Java or Scala code and SQL to complete a SQL job. We developed the DDL with Antler, which allows users to develop a streaming job only in SQL. StreamSQL has many advantages over low-level API. First of all, SQL is a declarative language and used by almost all developers. There is no need for them to learn native Flink API or connectors API or anything else. They could simply focus on processing data. Secondly, SQL standard is stable. Users do not care about which version of Flink the job is running on, so we can keep the version up to date every time the job is restarted. Thirdly, problems are easier to be located and solved. A low-level API, a low-level job is submitted as a jar file, and it's very hard to know the details in it. However, in StreamSQL, we can see all SQL codes, and the logic is under control. And therefore, it's much easier for us to locate and solve problems. And also, we can optimize the underlying logic to make the job running more effective, but do not affect the users. At last, as SQL is already widely used in batch processing, and it will be easy to unify batch and stream processing in SQL. We did the following to build StreamSQL. The first is to improve DDL. We can represent the input by writing SQL statements such as create table or create view. And for the record of JSON format, users can extract values by JSON path. StreamSQL supports various connectors, including Kafka and other message queues in DiDi as sources, and almost all the major storage systems as sinks. Besides Kafka and DDMQ, such as Druid, HBase, Elasticsearch, ClickHouse, MySQL, etc. Basically, users can connect to any of these data sources and sinks with StreamSQL, and no need to learn the various APIs. For the most popular data formats in DiDi, we have built in some parsers to simplify users' work. For instance, the binlog data, we extract all the business table fields, table name and the database name, then put them in a map so users can get values from the map via built-in functions and do not have to develop UDF to parse the original records. The second one is business logs, which have unified log format. We also built in parsers and extract all the business fields in a map. For the general record in JSON format, neither binlog nor standard business log, JSON path is recommended to extract the corresponding fields, which is easy to use. Lastly, for other records which are neither standard format nor common JSON format, they can be specified as string or even binary data. Nothing will be done to these data during consuming, and then users can write their own UDF to process their personalized data. Based on this work, it is convenient for our users to consume and deserialize data from table source, and there will be no need to define a deserialization schema, which significantly simplifies their work. Next is the extended UDF. There are three kinds of functions: built-in functions, user-defined functions, and compatible Hive functions. We collected frequently used functions in daily SQL jobs and put them in StreamSQL as built-in functions. And of course, these are not enough. Users can develop their own functions in Java or Scala, build them into a jar package, upload it to our real-time computing platform, and define a function with the create function SQL statement. The third kind of functions are Hive functions. Hive has been in production for many years, and many UDFs have been developed. If they can be reused, it will be much easier to develop a streaming job in StreamSQL, especially for Hive users. They do not have to develop UDFs for a second time. This idea is the same as what Flink community did, but the one we are using now was implemented earlier by ourselves. The last important point of StreamSQL is stream join. A stream table can join another stream table or a dimension table. As we all know, stream join is not exactly the same as batch join, and the join result is related to the order of data arrival. Based on the characteristics of our data and scenarios, we customized the implementation of stream join using states with TTL. When a stream table joins another, we cache all data from both streams in states. When a record arrives, it is stored in a state, and the corresponding record in the other state could be found with the join key and vice versa. When another record with the same key arrives, the value in the state will be overwritten because only the new record is needed in our scenario. Dimension table join is also supported. When a record arrives, the corresponding record will be searched in a dimension table, which is stored in a key value storage system like HBase or Redis or other similar systems. The key value store is searched through asynchronous I/O to reduce access latency and increase throughput, and old data is cached in state to avoid high TPS of KV stores. Now StreamSQL has been widely used. More than 5,000 streaming jobs, which is 80% of all the streaming jobs, are developed in StreamSQL. The third part of my talk is how we constructed our real-time computing platform. This is the IDE of StreamSQL, which contains plenty of functional modules, including SQL boilerplate, UDF library, intelligent prompting, and syntax checking. When you have checked the syntax and finish your SQL, you can debug it by consuming a sample data file and output it to the console. Then you will know whether the SQL met your expectation. This significantly shortens the SQL development process because you do not need to submit it to the cluster frequently. It supports version control as well. Users can revert their SQL to any previous version. Now, let's look at the job management. The web platform is the only way to submit a Flink job, and this eliminates the operation of Flink client. Every job has several phases during its life cycle, such as created, running, or stopped. As it supports version control of StreamSQL and Flink jar, users can upgrade their jobs or roll back. As we have no idea how many resources a streaming job will consume before it has been running for a while, the configuration of resources is usually not optimal at the beginning. So during the job's running, resource consumption will be collected and new configuration will be computed at the platform. And next time when the job restarts, the configuration will be much more reasonable. This helps improve our cluster resource utilization and load balancing. Now, the job operations. We have rich metrics in terms of the health of every running job, such as input records per second, latency, size of the states, etc. If a job is restarted due to errors, problems can be located by searching logs in Elasticsearch, since all logs have been collected to an ES cluster. And in terms of lineage tracing, every job has upstreams and downstreams, and they are also reported by the jobs as metrics. It is very easy to check where data comes from and where it is going. And when a job fails or logic is changed, it is also very easy for people to know what has happened and what will happen. Since streaming jobs are usually running around the clock, alarms are necessary. For instance, the latency checking, when the latency exceeds a certain threshold, it fires an alarm to notify users to solve it. There are also some other alarms, such as restarting check or checkpoint failures. Now let's have a look at the stream meta construction. Streaming data usually do not have schemas. Only the producers and a few consumers are familiar with the content of the data. This makes other users hard to find the data they needed, and it is difficult to build a real-time data warehouse based on these unknown data. So we built stream meta on this platform and make data easier to use. Before consuming a Kafka topic in a StreamSQL job, a stream table needs to be registered with fields definition according to the topic's data. After this registration, the fields from stream table can be selected the same way as Hive. This work eliminates the repetitive definition of stream source and manages all topics together. Based on different responsibility of different teams, we do not unify batch and stream processing at the engine level, but on the platform, we register all the meta information of batch tables and stream tables in Hive metastore and provide a unified view to users. So for the users, the batch table and stream table are the same, and the SQL can be executed by Flink or batch processing engines like Hive or Spark or Presto. We believe this will be the trend of big data processing. Okay, at last, let me introduce some challenges we are facing and our future work. One of our biggest challenges is the large state management. When the state grows larger, it could often introduce I/O problems when checkpointing and affect all jobs running on this node. And small state cannot support some computing scenarios and which requires a large amount of data over a long period, like a month. The second challenge is high availability. Some jobs are used for online business, so high availability is one of the most important things we should take into consideration. We should be able to recover a job from an old save point smoothly when it is upgraded, locate the problem's root cause as soon as possible, and scale resource smoothly. The last challenge is that multiple programming languages should be supported. Some of our users are not Java or Scala developers, but Python is widely used, so version 1.10 really helps a lot. In terms of our future work, first of all, we will work the same as before to continuously deliver a stable and efficient stream processing service. As we will also try to extend our work to real-time machine learning using Flink, using A-Link, and more real-time data warehouse scenarios. We hope Flink will play an increasingly important role in the future, and we think we could make it happen. Okay, thank you for listening, and again, I wish you all the best.